Last time we talked about kinetic energy, the energy of motion. And this time we're moving on to potential energy, which is stored energy. Specifically, we're going to be talking about gravitational potential energy. So gravitational potential energy is an object or system's stored energy based on its position above the surface of the Earth. Okay, and so the formula that we have for gravitational potential energy, we are going to use E sub G. Gravitational potential energy is equal to mass times 9.8, acceleration of gravity, times height above the surface of the Earth. Now you'll notice that up here it gives you several different notations for gravitational potential energy. UG is one of them. It's really common to say potential energy using the big letter U, and then G to make it specifically gravitational potential energy. You'll see that all over the place. This one maybe is a little bit less common, potential energy, specifically gravity. This one is the one we're using because it's consistent with the other notation that we're going to use in this unit. E for energy, and then we're differentiating the different types using a subscript. And then this last one over here would be general potential energy. But since we're talking about gravitational potential energy, I like E sub G better. Okay, now we can derive this formula in a simple way for our purposes, using just the same kind of strategy that we used for kinetic energy. So work is a change in energy, right? So work is equal to force times displacement. Okay, and so in our circumstance, we're going for change in gravitational potential energy is equal to work, and work is equal to force. So specifically, we're talking about the force of gravity times displacement. Okay, now we can replace this force of gravity with its formula. Now, earlier on in the year, we talked about universal gravitation, which is a little bit more complicated formula, but it works in all circumstances, whether you're near the surface of the Earth or on a completely different planet. But because we are going to be talking about gravitational potential energy near the surface of the Earth, we're going to talk about mass times 9.8. as the force of gravity. Okay, so we're simplifying it a little bit for specifically our purposes. So we're going to replace Fg with mass times the acceleration of gravity times displacement. And in this case, the displacement we're talking about is the distance you have been moved above the surface of the Earth. So this change in d is just height. Okay, and that's where our formula comes in. So the change in gravitational potential energy is work. Work is mass times 9.8 times the height you've moved above the Earth. And assuming that your initial height was 0, assuming that your initial gravitational potential energy was 0, then your formula for gravitational potential energy is just exactly this, mgh. Okay, now notice that I didn't put any vector symbols on any of those things. You don't need to. Gravitational potential energy is a scalar, it's not a vector, and so the direction that things are moving, that it doesn't really matter very much. We can figure that out in other ways. Okay, and so we're going to do just like we did for kinetic energy. We're going to assume that something's speed is not going to change. Okay. Right down here, note, in this formula, it is assumed the velocity of the object does not change. Okay, we looked specifically at kinetic energy last time, and we said we're going to ignore height changes because that would change gravitational potential energy. Now we're going to assume that when you are lifting something up or dropping something down, that you're not going to be changing its speed at all. So this kind of negates most real life circumstances. Anything that falls is changing its gravitational potential energy, but it's also changing its kinetic energy. So we're going to get to that. We're going to put all those things together, but we're just going to, for a moment, look at situations that only deal with gravitational potential energy. So keeping that in mind, we've got work is equal to a change in gravitational potential energy, which means that work is equal to final minus initial, Eg2 minus Eg1. When you exert a force that changes the height of an object, you are doing work, which results in a change in gravitational potential energy. But when you are unable to maintain that force, gravity tends to transfer your gravitational potential energy into kinetic energy. Now we're going to do one example here. How much work must be done to roll a 1,500 kilogram car up a 10-meter long ramp that is 2 meters high? Let's draw a picture to start off with. Here's our ramp. A 10-meter long ramp that is 2 meters high. This is 2 meters. This is 10 meters long. And so we're taking a car, which will be represented by this box with wheels, and we're pushing it up that ramp. Okay? Now we're assuming that it's starting at a height of 0 and it's moving to a height of 2 meters. So the fact that we're moving at 10 meters in total, that actually doesn't matter. So MGH, the H part is the height above the ground. It's not the 10-meter distance that it has traveled to get there. Okay? And so in order to figure out how much work was done, work is change in gravitational potential energy. Change in gravitational potential energy. Final minus initial. But since we're assuming that this car is starting on the ground, initial gravitational potential energy is 0. So in this case, the work that is done to move the car that distance and lift it that height is just final gravitational potential energy, because that's how much gravitational potential energy needs to be added to the car. So then we can just do work is mass times 9.8 times that 2 meters. This is 1,500 kilograms times 9.8 meters per second squared times 2 meters high. So the work that has to be done is 29,400 joules. 29,400 joules.